I'm currently a postdoc at the University of Sheffield, but what I'll be talking about is a work from my PhD, which I did at Warwick with James Commode, who's here. Part of my PhD, which was on atomistic modeling of fracture in iron. I'm not a mathematician, so the focus is going to be a bit different from the previous two talks, but I hope it's still interesting. A bit of context, my PhD was funded by a European project that I will focus on predicting long-term damage in reactor pressure vessel steel, which are a low concentration alloy of alpha iron that has a body-centered cubic structure. So BCC metals have a brittle to ductile transition temperature. So at low temperatures below that transition temperature, you can see brittle fracture if you apply loads on pre-existing cracks. So everything I'll be talking about is in the brittle regime. And the aim is to use atomistic modeling to predict critical stresses and energy barriers for propagation that can hopefully feed into larger scale models of ferritic seal. So how are they usually modeled atomistically? Well, the method you'll find in the literature a lot is quasi-static loading. So the setup you use is something like this Pac-Man structure you see here, where you make it by first starting with a bulk, and you have your crack tip position alpha, let's say the center being 0, and then you apply continuum linear elasticity. You've heard this in Matrix talk, and this displacements u of each atom depend on k, which is applied load, the Young's modulus in the denominator, and also the position with respect to your crack tip position alpha. That's the second, and other parameters. This is iron, so it's the anisotropic solution. So where, based on continuum theory, you expect the crack to propagate at a value called the Griffiths value, where the energy to open two new surfaces, to gamma is the surface energy to open a crack surface, versus competition of the elastic energy release, which is in the denominator. But in theory, an atomistic effect is that you have a range of values, known as the lattice trapping range, over which the crack is stable. So in the quasi-static loading simulations, what they do is start with a value of alpha and k for which the crack is stable, and then make small increases until you see the crack propagating, and that's an estimate for the upper limit of your lattice trapping. More systematic way of doing this is what Maciek spoke about. I'll briefly go through it in my more layman terms. So first, NC flex stands for numerical continuation plus flexible boundary conditions. So the flexible boundary condition aspect was introduced by Sinclair in 1978. So you introduced this buffer region, the green one, week 2, which are also held fixed at their continuum linear elastic solutions, but the forces that they experience feature in this relation of to define the crack tip position alpha, so a function of k and the forces there. So now you have an extended system where the degrees of freedom are not just the displacements of your region 1 atoms, but also alpha and k. And that's why you can use numerical continuation. So you start, like Maciek said, first finding one solution of alpha and k for which this is in equilibrium. Take a small step in k to find an adjacent solution, and then use the gradient with continuation. Map out all the values of alpha and k for which the crack is stable. So what does such a map look like? Look like this, where I've got alpha along the x, like that, and k applied stress on the right. So if I flip this, you get the plot that Maciek showed before, but it's just from his paper, just to demonstrate it. So now I've got alpha on the vertical axis and k on the horizontal axis. So what information can you get about this system? So first you get the lattice trapping range. So it's the value of k between which your solution, the equilibria exist. If you go below k minus, the crack's going to close. Above k plus, it's going to propagate. And this is where you have stable solutions. The branch where your alpha k is increasing with alpha are the stable solutions, whereas the branch where the k is decreasing with alpha increasing are transition states. And if you look at a fixed value of k, which is each of these colored lines, then the transition states along them stable branch. Am I allowed to call them branches? Or segments? So are the energy maxima that we're connected to. But once you have these NC flex plots, you don't actually have to do the nebs. You can just get the energy barriers directly from the plot. So this is the method we want to use. Now we need a potential for iron. So most of the quasi-static factor work done in the literature use embedded atom models for iron, and they compare various different EAMs. But even trying the best EAM from the literature for fracture gave me very chaotic NC flex curves. So they might be good for predicting the fracture, but then the moment you go into the details of transition states and stuff, it just was giving rubbish. So, and ideally we'd like to go to DFT level of accuracy, but of course that's too expensive. So that's where MLITs come in, because they're trained on a database of DFT data and can hopefully relate its accuracy. So there was a gap is a type of machine learning potential, stands for Gaussian approximation potential, based, lots of acronyms here, sorry, quantum expressive kind of density functional theory code database in the literature, which was trained and used for quasi-static fracture. But when I used it for NC flex, again, it didn't know enough about transition states to do well, so it wasn't performing very well. Also, gap was quite slow. So I reevaluated the database with consistent parameters, because that's important. Let's fit an ACE potential, which is atomic cluster expansion, and it's a faster than gap as well. And did some iterative learning. Ran NC flex, as you can see, it doesn't do very well. Take points from this. For 4 different types of crack systems, I'm using the notation of the crack surface in round brackets, crack front in the square brackets. So choose a configuration, then cut out the center bit to make a periodic system, evaluate that with DFT, put that back in, and do a cycle. So after about 4 of these cycles, I got it to give decent curves for one of the 4 crack systems. Later I'll show others, which I did later, but for now, to get some useful information, let's proceed with this crack system. So zooming into one period, which is an initial transition and final branch. So in the paper that Maciek and James did, they use a similar approach to Sinclair to find the energy barriers, where you partition the energy to 2 components. One's the contribution from region 1, where it's all relaxed, and then there's the unbounded term from the far field. And the far fields, and you compute the energy difference with respect to a reference. So those are the E naughts in the subscript. And because the far field's unbounded, they approximate it. You have to take this reference energy, and they approximate it to the first order with that. And that worked in that case, but when I applied it to iron, it didn't really work, because when I applied that same formula, you're getting final states above the transition states, which doesn't make sense. And this is because I'm using, probably, I'm guessing, because it's a really small size, but I can't really go to larger sizes because it's really expensive to use them, but it just doesn't converge. So this was an ideal. So instead, it would be nice to have a better ingredient, but what I did is a bit of a brute force way. I took each transition state's boundary condition, applied it to the corresponding initial and final states of the same K value, and re-relax it. So that makes a real consistent. And then I do get, and I'm plotting them all with respect to the initial state of that particular case. So that's why now I've got the initial states all zeroed. I'm plotting all the transition states with the consistent boundaries with respect to it. And you've got the energy as you expect. It's the highest barrier to crack propagation is at K minus, at the lower end of the lattice trapping range. When you go to K plus, it goes to 0 energy barrier. And then plotting the final energies, you get the crossing that you're expecting. So below a critical value of K, you've got the energy barrier like that, where the final energy is higher than the initial, and then the flip on the other side. And the critical KC is where you have a symmetric barrier. The initial and final states have equal energy, and you've got a barrier. So taking the KC configurations, you can now set up a 3D mechanism. And the reason I hesitated earlier when I said I extend proper 3D is because I'm now doing a NEB and not continuation. So I'm sorry to disappoint. I think you can do it with continuation, but given the convergence issues we had with just one, I think getting it to convert for, say, a 16 layer thing would have been, so it's more of a algorithm. I mean, I think continuation would be a neater solution, but for now I'm using this. So, but it's still useful because you get these transition states, which gives me a way to set up my initial guess for the NEB. So I'm guessing, so set up the first layer of the neb in this cartoon by stacking all the initial states, the last layer, neb image, stacking all the final states. And I'm proposing a kink mechanism here using my transition states. So you still have a start of the kink in the second neb image, 2 transition states, and then put some final states. So slowly progressing towards a final state. And let's see what you get with this. So unrelaxed pathway, just taking the 2D plane strain structures, making this, what does it look like? Kind of looks like you have that initial energy barrier and then it plateaus or the kink migrates. When I relax it with neb, get a similar plateau structure. So most of the energy seems to go in forming the kink, and then it plateaus out, and then it reaches the final state, which are the same energy. So this is what visualizing it looks like. So I've used the neb images. The first image, the color shows how close the atoms are to the initial versus final position. The initial layer, they're all a straight crack front. Final layer is also straight crack front, all dark blue because they're close to the initial position. The final layer is all yellow, straight crack front again, straight. If you look in between, you see the formation of a kink and it propagates out. So energy barriers with size, look at the size conversion again. So as I increase the number of layers in the 3D structure, which is the x-axis in the plot on the right, and I've put the 2D one just scaled with the size of your crack front, the straight crack front, but the 3D one plateaus out when your system is large enough. And if you look at the size of the kink, basically at smaller sizes, your cell's just not big enough to accommodate the kink, so it's going by straight crack. But once the system's large enough, it does, and that's more favorable because it's a fixed energy that can scale with your crack size. So all this was shown with a 30 Angstrom region 1 and the relevant cutoffs. What happens when you increase the size of region 1? Both energies go up. Increase the size further, it goes up even more. And plotting these values. So in all cases, for the low size of NZ, the 3D case, is straight crack and kink nucleation at larger sizes, that converges. But the region 1 size still doesn't seem to be converging. Or, well, it's increasing significantly. Plotting them out, we're still very far from what we can converge. So I've put region 1 radius of our in-plane on the x-axis, and the energy barrier, the so-called 2D. The 2D is actually 3D, it's just straight crack with periodic boundary conditions. And then the kink nucleation, and you can see we're far off, but I really could, the larger size simulations just struggle to converge and get anywhere. So now I have to rely on some extrapolation methods, which is good. For now I'm doing, since I'm assuming it'll converge, I'm doing an exponential fit. I think there might be better ways of doing this. But now I take the log and kind of take that intercept to get an estimate for a large size converged, hopefully, value for these barriers. Similarly, for the lattice trapping ranges, K minus K plus, the limits of your NC flux curves, as well as the critical stress intensity factor you get, they also have this convergence thing, and you can find a converged value by doing the same trick. One reference point, quasi-static fracture studies previously did show a similar value of 1.24, which agrees with this extrapolated value, so at least it's in the right ballpoint, even though we're using this extrapolation method. Briefly on what can we do with this, then we were hoping to parameterize a velocity model, so that depends on temperature and the stress intensity factor, so propose a model that. So using harmonic transition state theory, where we can write a frequency of probability of the crack propagating and the probability of crack retracting. And then we can compute these A's from the ratio of the frequencies of the transition state, initial state versus the transition state for the first term, and the final state versus the transition state for the second term. And Lx is the length scale along the crack propagation, which you multiply with the frequency to get your velocity. So again, now we have this A prefactor that you need to compute from the frequencies. And I it's another thing that has to converge with sides. And this time, okay, the values are huge there, but the LX is in angstroms, so that will cancel off, so it's okay. But doing the same exponential fit and log, it doesn't fit very well here, but I'm gonna use it. But I'm just doing it because I've done it for the other terms as well. I would like to fix that, but yeah, getting a value for A just to get what it looks like. So using that value of the prefactor, you can plot the velocities for various values of K. I realized I should have cut it off at nearly 200, maybe 200K, because by then ductility will kick in, because plastic, and that's not going to hold anymore, because this is all purely brittle fracture, because that's the transition temperature at a low strain rate for him. Okay, so that was all in my PhD. Recently, I did a refit, and everything I showed was for that one crack system. I recently did a refit and managed to get relatively smoother curves for the other 3 crack systems. And though you do have those features that you saw in Maciek's talk before for 2 of them. Doing the same thing of selecting some points. This time I take it in the center because we'll have to deal with those features later. But for now, I'll take the central bits. Do the same fixed BC trick and do the energies to find what's happening. Clearly in 2 of them, that doesn't make sense. When you extrapolate beyond the data points I've taken, it's not really working where you have the features, but in the central bits, you get similar behavior to before, even with this fixed BC trick. And if you take the energies at these KC values and do a size convergence again, you get similar behavior. You can compare the barriers for the 4 different crack systems. The barrier I get with this potential for the 100,001 crack is about half for than the other 3, which suggests that that's the most likely crack system where you see thermal fracture. And then looking at the lattice trapping ranges again, repeating it for these 3, and a comparison plot of the extrapolated values for the 4 different crack systems. You have the lowest ones being the same one with the lowest barrier, as well as 110,001, but that has a much higher barrier. That has the 3rd crack system has about double the energy barrier for the crack. So yeah, that's it. Some conclusions. I've used a machine learning intraatomic potential atomistic model fracture atomistically. Tried out NC Flex for it, which helps model the lattice trapping range more systematically, and got a way of extracting out 2D and straight crack energy barriers and kink energy barriers, and also a proposal for temperature and K-dependent crack velocity once you have these. Next steps, comparing these velocities with maybe ND and experiments, quite critically explaining all these extrapolation things I'm doing, which is very dissatisfying, but that's the only way I can get to larger sizes for now using NC Flex. And hopefully, instead of having to extrapolate it, we can improve the algorithm so that it can actually converge so that we don't have to extrapolate. That would be great. So that brings me to the end of my talk. I'd like to thank my PhD supervisor, Prof. James Colt, my second supervisor, Albert. Fraser Burks is here too for many very essential code developments in NC Flex on MathPy, and Maciek for lots of advice on NC Flex, and everyone in James's group during my PhD. I've not included Mars here, but Mars is also funding my my conference attendance, so thank you to Mars. And yeah, all my funding agency, both during my PhD, and I'm currently funded by UKAEA because I'll work on modeling. That's a whole different project, but yeah, if you're interested in collision cascades, including non-coarse graining, non-adiabatic effects into collision cascades, that's what I'm working on now. Very different from this. Couldn't put them both into the same talk, but yeah. Okay, thank you all for your time.